1800s. It was motivated by technology. People had just developed the steam engine and they wanted to figure out how efficiently it could pump water out of mines. So these practical questions ended up turning into a fundamental direction. People started asking, why does time flow in only one direction? And do materials consist of particles too small to see? So there's this balance between practical applications and fundamental physics. Thermodynamics was developed to describe the cutting edge technology of the day, the steam engine, namely large classical systems. Today's cutting edge technology looks a little bit different. Experimentalists today have great control over very small scales. For instance, this is a strand of DNA. You can take lasers and use them as tweezers to trap one end of the DNA and then stretch the other end. You can measure the work required to stretch the strand through a given distance. This is the dilution refrigerator used to cool down a quantum computer formed from superconducting qubits, very small circuits that serve as basic units of quantum information. Quantum systems were systems that the early thermodynamicists didn't know of or just barely started imagining. And again, this is a refrigerator, so it needs to cool systems down in order for them to be able to exhibit quantum phenomena, and cooling is a thermodynamic process that involves the exchange of energy. Relatedly, we're now interested in the interplay between energy processing and information processing. And also, we're often interested in far from equilibrium systems. And you and I, as living beings, are far from equilibrium systems, but also a lot of interesting far from equilibrium physics is being explored now in the quantum regime. For instance, at Harvard, some experiments involve closed quantum many body systems of many particles that you can poke so that they come out of equilibrium, and then you can watch as they equilibrate how information and energy spreads out across the system. All of these settings are quite different from the traditional thermodynamic setting that we just saw, but thermodynamic concepts such as heat, work, and efficiency remain relevant. So we need a toolkit for revamping thermodynamics for the 21st century. Quantum information theory offers such a toolkit. Quantum information theory is the study of how we can use quantum phenomena to process information in ways in which we can't with just classical systems like my computer. By process information, I mean solve computational problems, communicate information, secure information cryptographically, and store information in memories. And by quantum phenomena, I mean a range of behaviors. So entanglements, the non-commutation of operators or matrices, the discreteness of spectra, how a measurement can disturb a quantum system, and a bunch of other effects. Quantum information theory, like thermodynamics, in part has been motivated by technology, for instance, the promise of quantum computing. But whatever the initial reasons, now we have just this wonderful mathematical and conceptual toolkit that we can use to gain new lenses onto many fields across science. Condensed matter physics, high energy physics and black holes, computer science, atomic, molecular, and optical physics, and thermodynamics. So if you take the thermodynamics of the 1800s and re-envision it for the 21st century with quantum information science, you get this fusion of old and new that I like to call quantum steampunk. So here's where I'd like to go in the rest of the next half hour or so. First, I'll try to convince you that work and information can both serve as resources in both thermodynamics and computation. Then I'll talk a bit about how I got to where I am. And then there'll be a lot of time for questions and answers, but feel free to ask questions at any time during the talk. But let's see that you can turn information into work and vice versa. So the first part of the story features what's called Szilard's engine. So Szilard was a great Hungarian-American physicist of the 20th century. He argued that you can use information to turn heat into work. So heat and work are two types of energy that are exchanged between systems. Heat is work that's not very, heat is energy that's not very useful. It's random energy, it's uncoordinated, it's not being used to directly perform any useful task. Work is useful energy. It is coordinated, it's organized, it can be used to push a car up a hill or charge a battery. Let's imagine a classical particle in a box. This is going to be a very oversimplified version of an ideal gas. Suppose that this particle exchanges heat through the walls of the box with a temperature T heat path or environment. Suppose we begin with one bit of information about this gas. We know that the particle starts in the right-hand side of the box rather than the left-hand side. We can slide a partition into the box, then tie a rope to the partition and tie an Acme anvil to the rope. Then we can unfix the partition so that it can slide. This particle is going to punch the partition. It's going to keep punching the partition until the partition gets to the other side of the box. Now we have lifted the anvil. The anvil has gained potential energy because we've taken heat out of the heat bath and turned it into work. How much work can we perform? This type of work is pressure volume work. So it's the integral of from the gas's initial volume to its final volume. We all know the ideal gas law. So this is the pressure, this is the volume, this is the number of particles, which is in our oversimplified case is 1. This is Boltzmann's constant, a universal constant of nature, and this is the temperature of the heat bath. We can solve for the pressure in terms of the volume and substitute into our integral. So I'm integrating from v/2 to v because the particle begins confined to half the box, but ends up able to be anywhere in the whole box. So we integrate, we evaluate the limits, and we find that we can perform an amount of work that's Boltzmann's constant times the temperature times the natural log of 2. So that's how much work we can perform on the anvil, which is good, but we have lost our bit of information. By now we have no idea where in the box the particle is. So we've traded information for work. We can go the other way around. We can reverse Szilard's engine to perform what's called Landauer erasure. Landauer was an information theorist and a physicist at IBM. He was actually skeptical as to whether quantum computers could exist. Suppose that we begin with some potential energy, a lifted anvil, the capacity to perform work, and we have a particle in a box. We have no idea where the particle is. We want to reset the particle to have a well-defined position so that we know where it is. This is like taking a messy sheet of scrap paper and erasing it to a clean, well-defined state. We can slide a partition into the box and then squeeze the partition so that the gas ends up in the right-hand side of the box. Since we're compressing a gas, we have to perform work, at least KT log 2 units of work. And now we've returned the bit to the unknown state. So this is called bit reset or erasure. And this story has deep implications for the relationship between thermodynamics and computation. Suppose that we want to compute and compute and compute and compute. Eventually, we're going to run out of scrap paper. So we're going to have to erase some scrap paper. We've just seen that erasure costs work. So computation has a fundamental thermodynamic cost. When I first heard this story as a senior in college, it blew my mind, because who would have thought a priori that thermodynamics had anything to do with computation? But it turns out the two are very closely connected. Okay, this talk is called Quantum Steampunk, but I've been telling you about a classical gas in a box. So where is the quantumness? How can we put it in? I'm going to give a little bit of background. I'm going to talk about entanglement. So entanglement is a relationship that quantum particles can share. It manifests in strong correlations between the outcomes of measurements of particles that have shared entanglement. These correlations can be stronger than any correlations that you can create using just classical particles. For instance, suppose that I have a particle A and Gandalf has a particle B. We can bring the particles together and perform some operation on them so that they become entangled. Then we can bring the particles far apart. Suppose that Gandalf measures his particle locally. He has no idea which outcome he'll obtain. For instance, suppose that we have entangled the spins of 2 electrons, and suppose that Gandalf measures whether his particle's spin points upward or downward, then both options happen with probability 50%. Now, suppose that each of us measures our system locally, then there is a measurement that we can perform such that we can predict something about the joint outcome. Suppose that we both measure whether our particles' spins point upward. Then if Gandalf, well, now I'm going to make a specific assumption about what type of entangled state I'll have. For those of you familiar with the term, I'm going to assume that we hold in a singlet state. Then if Gandalf finds that his particle points downward, I'll find that mine points upward. And if his points upward, then mine will point downward. So these outcomes are correlated. Furthermore, there is a measurement that we can perform jointly on the entire system of both particles, such that we can predict the outcome exactly. So there's some information that isn't in Gandalf's particle, it isn't in my particle, and it isn't in the sum of the 2 individual particles. It's sort of spread between the particles. Or in the case of entanglement, the whole is greater than the sum of its parts. Let's apply that idea to erasure in thermodynamics. Suppose that the system we want to erase is not a classical particle in a box, but a qubit, a quantum 2-level system, basic unit of quantum information. For instance, suppose that we want to reset the spin of an electron so that it's pointing upward. Suppose that our system is entangled with an external memory. And again, we have a heat bath around that we can use. Then you can erase the system while keeping the memory in its same reduced state, while extracting net positive work. This result should contradict our intuitions. We just saw that erasure costs net positive work. But in this case, we can sort of burn the correlations between the system and memory. We can, in a sense, use the entanglement as a sort of thermodynamic fuel. In summary, we can use information to turn useless heats into useful work. And information, work, and entanglement can all serve as resources in both thermodynamics and computation. Does anyone have any questions at this point?
I have a quick question that's maybe, well, so I'm not too familiar with these systems, but could you maybe like briefly sketch like experimentally what like in your previous slide, maybe what this might look like in an experiment, like what the qubit might look like in the heat bath and the memory source, especially the memory. I'm not too familiar with like
this can be just another qubit.
Yeah.
So if this is an electron spin, this can be another electron spin. Electron spins often don't last very long in quantum settings. So this could be a nuclear spin, and this could be a nuclear spin.
And what would your heat bath sort of be, I guess?
This, for instance, could be some sort of environment, or one of my favorite examples is superconducting qubits, very, very small circuits that when cooled down to very low temperatures can exhibit quantum behaviors. So these could both be superconducting qubits. And suppose that you stick the superconducting qubits in a cavity in a box. The box has light in it, and the light can act as a heat bath. It sort of bathes the qubits.
I see. So like black body radiation or something, and then that would sort of black body radiation is a thermodynamic fuel in that case.
You can think of it roughly like that.
Okay.
Anybody else?
Yeah, sorry, just to double check. Is it kind of, are we kind of leaving it unspecified, like how the burning of the correlations can be used to extract work?
Yeah, here I'm not being too specific. Basically what happens is, so the protocol is, here you have a 2 qubit system, and you can, so these together form one well-known state. If they're in, I'm going to start using some words that some people might be unfamiliar with. So if these are maximally entangled, then they're in a pure state, which means you have a lot of information about them. There exists a measurement that you can perform such that you can predict the outcome exactly. Even though this system all by itself, if you look at it by itself, it looks totally random. So that was, and we would like to erase this state. So it by itself is in a pure state, in a well-defined initial state. This entire thing is a pure state. So we can basically run it through CLARD's engine. And so we have basically 2 bits or 2 qubits of information that we can put into our CLARD engine. So we can extract 2 units, Boltzmann's constant times temperature times log2 of work. And then we can use one of those units to erase this system by itself. This system is going to end up in a maximally mixed state, which is the state that it actually started with. It's just no longer going to be entangled with the system of interest. And the system of interest is going to be in the desired clean state, let's say pointing upward. So we extracted 2 units of work from this joint system, and then we spent one of those units of work in order to erase this system. So we have 1 unit of work left over.
I have another, sorry, if that question's finished, or I have another follow-up question on this. So once, it's not completely clear to me like what the, like what, this is a very dumb question, but like what is this work used for? Like I imagine in quantum, like some sort of like quantum computation or some sort of like, maybe you can like implement in some quantum algorithm or something, or
it depends on what you want to use it for. You could store it in a battery for a while, and then if you acquire enough energy, you can push a car up a hill, you can lift objects, you can run currents through wires, you can do anything that you can do with work. So you can make it electric work, electrochemical work, gravitational work. There are all sorts of things that you can do. Work is a thermodynamic resource. It's energy that you can use to power a computer, do anything for which you need readily available energy. If you use quantum systems to extract work from, then you're going to get very small amounts of work. But if you extract from enough systems, then the amount of work can add up.
Yeah. So since these are really like small amounts of work, which, I imagine you would need quite a few of these qubits, but one of the main concerns today, getting in like the quantum computing, is basically that we are not able to have very like large amounts of stable qubits. So the scalability is, again, like seems to be an issue with this system. Is
at
that
the moment
really an issue, or?
So there are a number of goals that you can have. At the moment in quantum thermodynamics, one of the main goals is basically to get a handle on quantum work. The amounts of work that you would extract from a quantum system would be quite small. So for instance, I'm not going to power my car, not that I own a car, but if I owned a car, then I would not want to power it with a quantum system because that would be impractical. But suppose that we just study quantum work in and of itself, then it turns out, so as I said earlier, we know that we can use quantum phenomena like entanglement in order to perform information processing tasks more effectively than we can if we use just classical systems. And information processing tasks include compressing information, sending information down wires, securing information. Just as there are information processing tasks, there are also thermodynamic tasks. Those include work extraction, the use of work in order to perform a useful task, the charging of batteries, the running of engines. And you might conjecture then that we could use quantum resources in order to perform these thermodynamic tasks better than we could with just classical resources, parallel to what's happening in information theory. And the answer is yes, you can use quantum phenomena to perform certain thermodynamic tasks better than in classical settings. So partially, people in quantum thermodynamics are just figuring out what the deal is with quantum work and heat, and also even how you define these quantities, which is not entirely clear. So in a lot of work is fundamental. We're looking for fundamental differences between classical and quantum. And we're also looking to see how can you even take some classical ideas like work and heat and define them and make them useful or basically just well-defined in a quantum setting. For instance, work and heat are defined somewhat straightforwardly in classical thermodynamics, but in quantum theory, systems don't always have well-defined energies at all. So how do you define a system's energy, let alone distinguish which energy that comes out we should classify as heat and which energy we should classify as work, and how do you even measure these energies? Since if you measure a quantum system, you'll change its energy probably. So these questions, again, are fundamental. So a lot of quantum thermodynamics is at the fundamental level, figuring out just what happens and how does classical differ from quantum. So when it comes to work extraction, again, this is not something that the quantum setting is not the setting that I would want to use in order to power a car or my classical laptop. But once we figure out things on a fundamental level, then we can look for classical applications. So that's one branch of research that I've started looking to try to take quantum thermodynamics and not only gain insights into the physical world, which is most of quantum thermodynamics, but actually do something practical and technologically useful. So hopefully I'll have something to report about that in a few months.
Yeah, that makes a lot of sense. Thank you.
Hi, I also have a quick question. Sorry, a lot of questions right now. I've heard that measurement comes at the cost of entanglement quite often. Is it possible to select the cost to be thermodynamic costs instead of entanglement cost for information extraction from the system?
Entanglements and thermodynamic work are involved in measurements. What exactly measurement has an entanglement cost means, maybe we'd have to discuss. I can imagine some possible meanings for the term. Also, measuring a system can cost thermodynamic work. For instance, there's a paper that won the Paul Ehrenfest Prize recently for a paper on fundamental quantum physics that shows that if you want to measure a system's energy completely precisely, then you have to spend an infinite amount of work. And also, in a more general sense, suppose that you have a quantum system that is in some quantum state. It could be a superposition of energy eigenstates. And if you measure the energy, then you collapse the quantum states onto one energy eigenstate. And it could be a high energy eigenstate, in which case, in some sense, you're sort of putting work into the system when you measure it. So definitely thermodynamic work is a cost that we have to take into account if we're interested in tracking the energetics of measurements.
Thank you.
Sure. Okay, so let's shift from the mostly scientific part of this talk to the other part that I was asked to present. Who am I and how did I get to be here? I'm originally from Florida, which is kind of odd. Most people tell me that I'm more of a Northeastern sort of person. In a sense, I am, I think. For instance, a lot of people think that because I grew up in Florida, I grew up on the beach and spending a lot of time on the beach. I actually didn't. My family went maybe once per summer. But there is one aspect of being a Floridian that is very close to my heart. I have this superpower, as my best friend calls it, of being able to withstand high degrees of heat and humidity, which is useful, for instance, in Cambridge in the summertime. I went to the Northeast for college. I went to Dartmouth, which is very, very cold. So I acquired a lot of very warm layers. At Dartmouth, I wanted to take complete advantage of a liberal arts education. So I studied everything from economics to psychology to art history to German literature, in addition to biology and chemistry and computer science and physics. I just wanted to study everything. I didn't want to pick a major. But I found my way, fortunately, to the physics department. Of course, I loved physics too. And shortly after I took a class there, I found some professors who who embraced the idea of looking at physics from many different perspectives. And I found that if I study physics, then I can, in a sense, do everything. We, as physicists, need to use mathematics. We need to know our history. What did Bohr say to Einstein about quantum theory? We interface with chemistry and computer science. We write, we communicate. So this is a very rich field. And I'm grateful that I had the opportunity to construct a major with the help of the faculty there called Physics Modified. So this was partway between the physics major and the create your own major. I took a bunch of prerequisites in various subjects. I took some upper level physics courses, and I took some math, philosophy, and history courses and got to call that a major. By the end of this sort of multifaceted journey, I came to realize that it was physics that I really wanted to delve into in great depth. It was at the end of college that I found my way to this intersection of quantum information and thermodynamics. Senior year of college, took my first quantum computation course, and in one lecture, my professor presented Landau erasure, which I showed you. And as I said, that blew my mind. I just loved this intersection. I also loved the feel of linear algebra. I liked how quantum information sits on the border between fundamental physics and technological applications. I'd always been drawn to philosophy and very pure ideas, so I liked the idea of working in fundamental physics. But it is, and also philosophy and working with pure ideas is extremely important. But in some sense, it was relatively easy for me to convince myself that I was doing something directly useful, if I could say that I was working on a field that has applications. So philosophy is just useful in a different way from technological applications, and quantum information has both. So I grew very interested in this intersection. I needed to do some research. I had refused to do any conventional science research in college because it seemed extremely obscure. So partway through undergrad, I was standing in front of the office of one of my mentors. He had tacked up a paper that he was particularly proud of outside of his door, and I laughed at it. He didn't take this too badly. We got along very well, and now we're very good friends. But I didn't understand any of it. And I was a good deal of the way through a college education. And I thought, if I can't understand this, as someone who has most of a good college education, then it's just too obscure to be important, probably. I changed my mind. As I said, by the end of college, I became interested in delving into physics deeply. So I needed to try out physics research. The year after college, I moved to the United Kingdom and worked at Lancaster University as a research assistant. The Lancaster University, you might not have heard of, but it had an extremely good, physics research, especially in condensed matter. So I did theory in condensed matter and quantum optics. I was privileged enough to work with a really wonderful professor, Henning Schomeris, who is a fantastic physicist and also a really wonderful human being. Also, I had the privilege of living a few minutes from a castle built in the year 1000, so that was definitely a plus. So after working at Lancaster, I moved to the Perimeter Institute for Theoretical Physics in Waterloo, Canada, to participate in the one-year Perimeter Scholars International Master's Program. Waterloo is very cold, so I just kept moving from cold place in New Hampshire to Northern England to Waterloo, from cold place to cold place to cold place. And Perimeter Scholars International has a reputation for being very intense. It is a well-deserved reputation. It was extremely intense, but I'm very, very grateful to have had that experience. It was really useful for learning what it is to think as a theoretical physicist. Also, it was at Perimeter that I started working on the intersection of quantum information and thermodynamics. I was very grateful to undertake a research project with Rob Speckens, who is on the faculty, and Marcus Mueller, who was a postdoc there. We worked on a research project that ended up turning into a paper. And when that project ended, it led naturally into another project that I took into my PhD, for which I went to Caltech. So I finally returned to the sunshine, which made me happy in a way. My advisor was John Presco, who has contributed foundationally to quantum computing and especially quantum error correction and the application of quantum theory or quantum information theory to condensed matter and high energy physics. I said, John, I really love this intersection of quantum information and thermodynamics. He said, okay, go do it. So that's what I did for the next 5 years. There always seemed to be some other collaborator to work with and some new question to answer. So I really had a lot of fun, and John provided a lot of freedom in finding and working on projects that excited me. So I really delved into this intersection of quantum information and thermodynamics, and also with John's encouragement, broadened my view to see how this intersection could come to bear on other fields in which quantum physics, information, and energy are important. So how can we apply the tools of quantum thermodynamics to condensed matter, atomic, molecular, and optical physics, black holes, and so on? I'm very, very, very grateful for this opportunity. The PhD was a lot of fun, and it was during my PhD that I realized that the intersection of quantum information and thermodynamics has the aesthetic of steampunk. So I started writing about that on our blog. So Caltech has an Institute for Quantum Information and Matter, which has a blog that I've now written for since 2013. So I'm actually about to write my 100th blog post that will happen in September. It's been also a really wonderful privilege for thinking outside the box about physics. Physicists are supposed to be very creative, but there are some things that even we aren't allowed to put into papers. But the blog is a wonderful forum for making all sorts of crazy connections, including this one to literature and film and art. After my PhD, I moved to ITAMP, the Institute for Theoretical Atomic, Molecular, and Optical Physics. So this is an institute shared by the Smithsonian Institution and Harvard. The Smithsonian you might know as the national set of museums of the United States. A lot of those museums are in Washington, DC. A lot of people don't know that the Smithsonian also has libraries and does research. A lot of that research happens here on the edge of Harvard's campus, including at ITAMP. I've been very, very grateful for the opportunity to be here. The past 3 years have been a lot of fun. I've especially branched out in working with experimentalists, which has been very rewarding. Also, from a different perspective, one aspect of growth that I experienced at ITAMP was I fell in love and got married. So this is a picture from my wedding, which happened last year, right after the lockdown lifted enough that we were allowed to gather 10 people in the same place outside. So the masks are not shown in this picture, but they are shown in plenty of other pictures from our wedding. So my husband was an undergrad actually at Harvard when I was an undergrad at Dartmouth. We met senior year of college, but we didn't really have the chance to get to know each other very well because we lived 3 hours apart and I was always busy with schoolwork. I mean, he was busy too, but I was probably more busy and even more protective of my time. But we kept in touch over the years. And when I moved to Harvard Square for my postdoc fellowship, he was in some sense waiting there. He had never moved away from Harvard. So we got to know each other actually properly this time. And so that has been one wonderful benefit of being in the Harvard area. At the moment, I'm transitioning to a position at the National Institute of Standards and Technology, NIST. NIST does a lot of fundamental research, and it's invested a great deal in quantum information since long before investing in quantum information was cool. But NIST has a number of partnerships actually, with the University of Maryland. The two of them share a couple of quantum institutes. The University of Maryland also has some other quantum centers, and it has this interdisciplinary institute, which has a lot of thermodynamics. I'd, over the years, spent a lot of time visiting the University of Maryland because of this sort of ecosystem of quantum information and thermodynamics. So I was really thrilled to have the opportunity to join. So I'm starting a research group there. This is our webpage, the Quantum Steampunk Laboratory. It's based on the University of Maryland campus, where a lot of NIST people are all the time, even though we have NIST affiliations. And one more thing that came up during my postdoc fellowship was I ended up writing a book during the past year, sort of unexpectedly. I had done a lot of blogging and some occasional one-off pieces, for instance, for Scientific American, which generated this image, which was shown at the beginning of my talk. And an editor at Johns Hopkins University Press asked me if I was interested in writing a book proposal. I had not expected to write a nonfiction book, but it's been a really fun process during the past year. The book was just announced publicly and it's available for pre-ordering. Really, it's written for people exactly like you, which is one of the reasons why I was really happy to receive the invitation for this talk, because I had just spent quite a few months thinking about topics that are of the sort that are supposed to be in this talk series. This book is in large part about the landscape of quantum steampunk, quantum information and thermodynamics. But the science is put together with stories and including about my career and how I got to where I am. So it's really intended for exactly people who come to these talks, people who aren't necessarily experts yet in quantum information or thermodynamics, but who are curious and interested and thoughtful people. So if you're interested in hearing more after this talk ends about the topics in this series, then if you're interested, check out this book, because again, it was exactly intended for people interested in this sort of talk series. So thanks again. And if anyone has any other questions, then feel free to shout out.
Yes, I still have a question about back to the actual presentation about how work is extracted from the entanglement. Like what was that one thing that makes work come out of the system?
So let me go back to that slide. Here you have a system of interests, a qubit that you would like to erase. And here you have a memory, which could be another qubit. So that these two are maximally entangled. And if you write down the quantum state of this system all by itself, then it's a maximally mixed state, which means if you perform any measurements on this system, then you have no idea which outcome you'll obtain. We would like to reset this system. And that state is represented by the point at the center of this sphere. So we would like to reset this system's quantum state to the analog, the quantum analog of the states of a classical particle in a box, such that the particle is definitely in the right-hand side. And the analog, the quantum analog of that state is a state that's called the quantum zero state. It's represented by an arrow pointing straight upwards. So this is a pure state, and it is a state such that there's a measurement you can perform such that you can predict the outcome exactly. So you want to erase this system. Now this system and this memory, or a part of this memory, depending on how large the memory is, they are jointly in a pure state. So you have a bunch of information about this joint system because of the entanglement. The entanglement makes these two be in a pure state, a state about which you have a lot of information. If you have a lot of information, then we saw that you can turn this information into work via Szilard's engine and a heat bath. So here you have two qubits. So using Szilard's engine, you can turn these two qubits into 2 units of work. Then at the end of this process, this system will be in a maximally mixed state. This system will be in a maximally mixed state. They'll just no longer be entangled with each other. You can use one of those units of work to erase this system via Landau erasure. So you extracted 2 units of work, then you spent 1 unit of work on erasing the system of interest, and you're left with 1 unit of work.
Yeah, that's a little bit more clear. Thanks.
Sure.
I have a question that's more like a life question. So you said that you had like many interests in college. That's also, I feel like, very me. I also have many interests. I do theater, I do writing and poetry and all that. And I was curious if you had, like, if you follow those interests in your career today. Obviously, you've done writing. But how do you balance everything when you have a professional career in science?
That's changed over time. So I regarded college as an opportunity to acquire knowledge broadly. And then when I decided that in grad school, I really needed to focus. So I did focus very hard. The vast majority of my day was spent on physics. Writing was the one non-physics thing that I kept as something that I did regularly and dedicated some time to. Physics absolutely came first. And I basically wrote one blog post per month, which was just a small amount of time, but it kept that other interest going. And I did give up a lot to do with my other interests. For instance, I had friends who would take language classes at Caltech. I was invited to take humanities classes at Caltech, and those opportunities were tempting, but I thought, now is the time when I really need to focus. Grad school is a time to focus. So I didn't take advantage of those opportunities. I did a few little things here and there. So after courses ended for me, I would read magical realism before going to bed. And if I was in, say, London for a conference, then I would absolutely spend several hours during the weekend at the British Museum, because I love the art history of the ancient Near East and ancient Egypt. And so the British Museum is sort of heaven for me. So I mainly shut off the other interests, but I pushed hard into physics and writing. And doing that later gave me the freedom to expand again. After a few years of my PhD, I had focused on one aspect of quantum information and thermodynamics. And my advisor, John Preskill, said to me, this is good work that you've done, but now I want for you to think bigger. And he actually encouraged me to take on projects in condensed matter, atomic molecular and optical physics, and biophysics. So I started expanding again within the sciences. And that turned out to be something that other people encouraged me to do, that they sort of during the job application process recently, some people at departments said that they thought was valuable. So that was within science and within my research. Then I'm still not taking humanities courses, but I have a little more freedom in, let's say, going to museums on weekends. And I've been writing about art history, say, so those interests haven't gone away. They're not present in my life in quite the way that they were in college, but it's because I focused on physics and writing that I ended up with the freedom to explore chemistry and condensed matter and atomic molecular and optical physics. And then in my writing, for instance, in my book, I do a lot of exploring of poetry and novels and art history and so on. So it's been more of a focused, let's say, conscious engagement with other subjects.
That was very interesting to hear. Thank you.
Sure.
Also, it was a wonderful talk. Thank you so much.
Well, thanks very much.
I just have a quick question out of curiosity. So was your writing like fiction or nonfiction that you were involved in before? And do you have any plans? You wrote a nonfiction book recently, but do you have any plans to publish another, like, I don't know, maybe steampunk fiction book? I don't know.
Actually, in college, I wrote a novel, and then after college, the year I was doing research in Lancaster, I also had a fellowship to edit that book and to write a prequel, which I did. They haven't been published. I got to the point of, I sent my first novel to some literary agents, and I got to the point of getting personalized complimentary rejection letters, which I was very proud of. And then when I went into grad school, I said, I can't do this anymore because I need to invest my creative energies in research, which I definitely think was necessary. And again, still research is absolutely number one in my life. But if some literary agents happens to read my nonfiction book and think it would be a good idea to write a quantum steampunk novel, then I would be interested in hearing from said literary agent and seeing what that possibility could look like. And the book writing really, even in college and now, it's been really useful for research. So it's not something that's detracted, but it's given me ideas. It's definitely enhanced my understanding of quantum thermodynamics. So I've been grateful for the opportunity from multiple perspectives.
Yeah, and on the topic, or well, maybe I should get the book and read it, but I don't know if your book goes into it, but I'm interested in the prospects for this field, which you touched upon in a previous answer to one of your questions. And I know you said that it might take a little bit of time before you have a grasp on like what these like quantum units of work, I guess I'd call it, might be useful for. But do you have any like indications or like any applications that you suspect that this might be, that these like really, I guess I'd say like small like units of work that you can extract from like a system that you were describing? With the the qubits and the memory and the 2 qubits and the heat bath. Do you have any indications of what application, where that might be applied? Like probably not like lifting a car up a hill or something, or driving like that kind of like macro engine. But I don't know. Do you have any insight into that?
Yeah, and yes, the opportunities, what I see ahead for the field is definitely in the book. I am working on one project in this direction. Unfortunately, I have, well, it's not really unfortunately, it was just a request. I have a collaborator who asked that I not talk about it until the paper is out. So hopefully I'll be able to update you in a few months. But I think that is one of the great opportunities for the field. The field has provided a lot of fundamental insights. Like how do we take these classical laws of thermodynamics and reformulate them in ways that are relevant at all to quantum systems? And then what can quantum systems do better in thermodynamics than classical systems? So quantum thermodynamics has provided interesting insights into the nature of the universe, and so has classical thermodynamics. Classical thermodynamics also has covered useful systems like steam engines. And I don't know whether quantum thermodynamics will give us a new steam engine that will lead to a new industrial revolution, but I do have hope and at least one idea for how quantum thermodynamics can be useful. And I know that I'm not the only person thinking about this.
Yeah, that makes a lot of sense. And I was wondering if, so the like main example that you were using in your talk was the main draw from classical thermodynamics was like this Szilard engine, right? Are there other, I mean, there must be other, in ways from classical thermodynamics to, the quantum world, as it were, other than say like heat engines. So maybe is there, especially in like maybe like the theory, maybe like the mathematical formalism or something, maybe there's some way that you can apply like, who knows, like a partition function or something to some like quantum ensemble of particles. I don't know. What are the other sort of connections between the two fields, like beyond like just like a heat engine, something like that?
Yeah, I have a map that I sometimes use for the landscape of quantum steampunk. Let me see if well, no, I might have to dig for it for a few minutes. But this is, so what are the many different connections that you can draw between classical and quantum thermodynamics? It seems you might be asking, or what are the many different ways that you can take classical thermodynamics and make it quantum in an interesting way? I think of those connections as forming sort of landscape on a map, and also this is talked about a great deal in the book. So a map will show different villages and cities and towns and kingdoms. And I think of those as different subcommunities within quantum thermodynamics, which all have different perspectives and toolkits and favorite ideas. One of those towns is the town of quantum thermal machines, which includes engines, batteries, clocks, although I sort of think of quantum clocks as its own town or subtown because it's sort of a separate idea, or really autonomous quantum clocks, as well as refrigerators and ratchets and diodes. Then there's another subfield of fluctuation relations. So these are strengthenings of the second law of thermodynamics. So the second law is an inequality. It becomes an equality just at equilibrium. And so the inequality states that or one way to phrase it is the entropy of every closed isolated system increases monotonically. We can derive more detailed statements that are more precise. They provide us with more information and are stronger because they're equalities even far from equilibrium. These are called fluctuation relations. They originated in classical statistical mechanics. For instance, they govern the work that you have to perform to stretch a strand of DNA of the sort that I showed at the beginning of the talk. And quantum versions of these have been derived. There's also the sort of kingdom of one-shot statistical mechanics or one-shot thermodynamics. When we do thermodynamics traditionally, we think about the thermodynamic limits, which is a limit in which the number of particles and the volume of the system approach infinity as the ratio of the particle number to volume remains constant. I've never seen infinity particles. And sometimes it's useful to consider small numbers. In the infinite system limits, we get to think a lot about averages, and we can deal easily with averages in many situations, but sometimes we don't care about the averages. Sometimes you have one shot, and that's the shot that really matters. And it's probably not going to be the average. So there are mathematical tools, both from quantum information theory and also from the theory of large deviations that can be applied in that setting to both classical small scale systems and to quantum systems. So there are all these different sub-communities of quantum thermodynamics that have different takes on the field.
That definitely makes a lot of sense. Yeah, and we're coming up near the end of our time, but one question, for those, maybe some of those in the call don't know the tradition, but one of the quick questions that we ask our speakers last is if you have any words of advice for young physicists looking to start their journey through physics.
Have fun. Physics can be a lot of fun. It's not fun every minute, but hopefully it's fun at a sufficiently coarse-grained scale. So just really enjoy what you do.
Absolutely. And yeah, actually, I just have one more question of curiosity, and I've been dying to ask. But the picture that's illustrated in your background,
Oh yes.
is that of any particular, special? Did someone design that, or did you design that maybe, or what is it? And what is it a design of?
It's supposed to be a quantum steampunk sculpture. Last year, I was contacted by a steampunk artist about whether I would like to collaborate on a quantum steampunk sculpture. I never received any such request before, but it's been fun. So this is in the middle here, a quantum engine that manifests as a trapped ion. And then out here, this larger part is supposed to illustrate the classical version of the engine. So this is the design of the sculpture, and we're looking for a source for funding.
Yeah.
So hopefully it will exist outside of Zoom one day.
Yeah, I hope so too. That's really great. Okay, so yeah, thank you so much to Professor Yunger Halpern for the excellent talk. It was extremely engaging. It was really a pleasure to hear about your career and your research interests.
Thank you again for hosting me.
Absolutely, yeah, it was a wonderful talk. And thank you to all of you for coming as well. For the next few weeks of Quantum Summer, we have a really exciting lineup of speakers, including next week, Emmanuel Bloch of Max Planck, Michel Devoret of Yale, Junier of CU Boulder, Monica Schleier-Smith of Stanford, and many more. Okay, I hope to see you all next week. Again, thank you very much.